you guys see my screen?
Yep.
Yeah.
Okay. All right. Before I start writing like code and everything, I just want to do like or review what was covered last time because I'll be like building off of that. So basically, whenever you create a thread, you create TCBs, which are thread control blocks, and they hold the context of a thread. And context just means like values, the stack, and so on. Whenever you create a thread, the TCB, and depending on the priority, the TCB of that thread gets added. So the add task goes to priority 0 according to this code right here. And then this multiply task is priority 1. And the subtract task is priority 3. And there's always an idle task, or you should always make an idle task with the lowest priority. Sometimes OSs will create an idle task for you, like inside their initialization. So you don't have to add it yourself, but some OSs you may need to add it yourself. So it just depends.
I think Micrium has it optional, but don't quote me on that.
Yeah, I think it is optional, but if you do want the RTOS like underneath the hood to create it for you,
there's some flag you have to set.
Yeah. And then, so whenever you have a blocking function, so like pretty much you're waiting for a semaphore or a resource, it pretty much goes into like this list of blocks TCBs. I'll show like what the actual implementation looks like. And then, yeah, I guess, does anyone have any questions before I start going to code? Okay, let me switch over to okay. So I have this template. It's on the Google Drive. It's in the link that I sent out. If anyone is interested in making having a template to make their own. Basically, I just want to first point out that there's some helper functions that I'm assuming that I have here that I have not implemented, mainly because I don't feel like writing this code and debugging it and whatnot. But basically, I'm just going to assume that this works. And so, okay, and then I'll just get into it. So, but pretty much in RTOS, you can think of it as like a state machine of handling linked lists. So the TCBs I mentioned earlier that holds the context of everything, that is pretty much a node. And the RTOS is pretty much, I guess, configuring that node, moving it around depending on where the priority or if it's blocked or anything like that. So just have to keep a note that an RTOS is literally just handling a bunch of linked lists. Okay. All right. I mentioned how TCBs they hold all the context, but the context of the thread or all the necessary information. So that can include an ID of the thread if you need to check the ID later. Priority of the thread. And then I mentioned how each thread has its own context, meaning the CPU state. So the CPU state holds all the registers, or the CPU state includes the registers R0 through R15, the LR, PSR registers, PC registers, and so forth. and also the stack. So the TCB, I mentioned previously that all those registers are pushed onto the stack, but I will go over it more in detail once I start writing that part of the code. But we specific for the TCB itself, to know the context, we just mainly need to know the stack. So we just need to know the stack pointer. There's some, and then I mentioned how TCBs are pretty much a linked list. So it's just going. So I think will be next. To make it easier, you can do previous to make some operations all of one instead of like if you have to like add it at the very end or whatnot. Yeah, this is pretty much. There's more information that you can add, like a sleep counter if you're going to have sleep capability and whatnot. For now, I'm not going to mess with sleep, but I will show you like how to get started on that if you do want to implement yourself. Anyone have any questions about TCBs? Quick note, if you're working on like a general purpose OS like Linux, you won't see TCBs, you'll see PCBs, which means process control block. And for IDs, they use PIDs, which all these terms are becoming redundant. Or like there's a lot of terms that means different things. But just a quick note, PCB, it can also mean process control block in terms of an OS. All right, and then real quick, I'm just going to fill this out. So there's always going to be an OS, or not always, but usually there's going to be an OS init function. You need to just call that at the very beginning. It's just initializing like the necessary like drivers and whatnot. And then you need an OS add thread, pretty much just creating a thread to run. In terms of Micrium, you pass in the TCB. So you pretty much allocate a TCB, a variable, and then you pass in the address of that variable. Then usually you need to, almost always, you're going to have to put in like a function pointer. Pretty much you can actually use functions as variables. And priority, and then the stack, and then the stack size. Just to note, I'm mismatching, like using the standard integer library and just regular ints. These don't really matter. When I use ints, they don't really matter. But for like the stack, I have a specific initialized to be a 32-bit, like so that it's accessible by word. Oops. So whenever you're, I guess, initializing or creating a thread, you're going to pretty much have to allocate or create a variable and then initialize your own stack size. So, and then once you like create your own threads or create all the threads, you need to have an OS launch function to actually begin the OS. And real quick, if there's anything that doesn't make sense, then just let me know, and you can just stop me. Okay. So I mentioned how you need to, most likely you have to call OS init function at the beginning. That's mainly just like initializing like the sysdig interrupt. And then also we have another interrupt that I mentioned previously called the PendusV handler. It's pretty much, the PendusV handler is a software triggered interrupt. So if you set a specific bit, then it will trigger that interrupt. And I have this defined right here. This is for the TM4C, so if it won't work for the STM. But pretty much to initialize PNSV, it's already initialized for you. You just have to set the priority. And the PNSV interrupt should always be the lowest priority because you don't want to do a context switch. So like you don't want to have like an interrupt running for one thread and then suddenly do a context switch, messing up all the registers. So I just have it like priority 7 for now. And then this is the register I'm talking. I mentioned how to actually trigger the PNSV handler interrupt. It'll be some type of control register, NVIC control register, similar to like how the SysTick registers were. There's just a specific bit that you have to set in order to trigger it. So right here, usually, and so in PNS and OS, and then you usually have to usually initialize the PNSV handler and also any timers like SysTick, and if you want to have sleep capabilities, and then any other like global variables that you have whenever you like make a more advanced RTOS. Right now, I'm only going to implement a priority schedule, just like a single priority scheduler, no hybrid and so forth. All right, real quick, just to, and also I just want to show that I have this assembly file to implement the PNSV handler and this OS boot, which I'll mention in a bit. But here it showed I have like disable, enable interrupts, and then start critical and end critical. This will be more important. And this is important in terms of like to make everything atomic. And just as a reminder, having an atomic function just means that whenever you start this function, or whenever you start executing this line of code, it's always going to end it's always going to end without any interruption in between. Start critical and end critical just means that disable and enable, whenever you call it disable, it will always disable it. But in terms of start critical and end critical, start critical just means that it's going to save. So whatever the interrupt or whatever, I guess, state the interrupts are, so if it's either disabled or enabled, it'll save that. And then end critical will pretty much restore the state of the interrupts. So say you have interrupts disabled, like for some reason, and then you have like an atomic function, you don't want to enable it again because your application disabled it previously. So pretty much start critical will see that, will save and see that it was disabled previously. And then whenever it ends the critical statement, it's going to see that it shouldn't be enabled because the previous state was disabled. Did that make sense? I don't know if that made sense, but let me know if it doesn't make sense.
What does the MRS and MSR commands do?
They're pretty much like it's like a red. I think. Gosh, hold up. So some instructions, if I remember correctly, requires like. Or actually, hold up. I'm thinking of something else. I don't know. I think it's something to do with like privilege level of getting a specific register that shouldn't be really accessible. I can get back to you later after this, Rishi. Sorry, I don't have a definitive answer.
No, I just never seen it before. I was wondering.
Okay. But usually all the OS functions should be atomic, so meaning that you should always, I guess in OS and you should actually always disable interrupts. And then whenever you launch, you should enable interrupts again. But in OS add thread, you should always make all these functions atomic.
For those who are wondering, MRS moves the PSR to a general purpose status register.
Oh, sweet. Thanks, Chase. Let's see. So I mentioned how the context is stored in the TCB, but inside the TCB, it's actually really stored in the stack. Okay. So whenever you're doing context switch, all the registers, all the general purpose ones, so R0 through R15, and then this one extra register, which is the PSR, the status register. So like whenever you're doing branches, that register holds like the N, V, and P bits. It's if it's like negative, positive, or zero, or does it Z? I think so. But anyway, we need to save that as well. So these registers, they all have to be saved. And to save it, we just push it onto the stack. Usually, whenever we create a thread, we initialize the stack. So that the state of this, or I guess, if you look at the stack, it'll look like this, pretty much. Specifically, the reason why it looks like, so you'll see like it's R4 through R11, and then R0 to R3, R12, and then the rest of these. It's because when a context switch happens in terms of an interrupt, and whenever an interrupt occurs, right before the handler gets called, the processor automatically pushes R0 through R3, R12, LR, PC, and PSR. So pretty much these registers here. So, so this is what the interrupt does. For the RTOS to save the whole context, I guess the user inside the PennSV handler must save this. And I'll show that in a bit. But that's the reason why it's sort of weird, why like R4 to R11 is pushed after R0 and so forth. But we have to just make sure that this is all, I guess. This is the state, or the state of the registers whenever there's a context switch. Usually for a second, it's I'm not going to write everything, but usually we just put in just dummy values. There's this specific dummy value. Don't remember what, it doesn't really matter. But this is the PSR. This is PC. PC, actually I need to add an extra input parameter. To add the task that's going to be run. Okay, so whenever you initialize a thread, and then whenever the OS launches, the OS will, I guess, want to know the task specific, like which task to run specifically. It'll know that it should go to PC, or the PC register will be filled with whatever address you last left off at. So whenever we initialize, we just save the PC. So whatever the register or the address of this task function will just be saved at the PC. So whenever the interrupt is popping all the registers, PC will get the register of this. Did that make sense? And then I guess one more important one. So the thing is, LR is null, or you can set to any variable or any address or number. The thing is, say we didn't have this, have a while loop. So say the function will actually end. Whenever the thing is at the very end, and like at the very end, and like if you look at the assembly code, it's going to call bxLR in this function. The thing is, LR, if you initialize the stack to look like this, LR will be like, if I set to 0, then it's going to jump to 0. So usually it's good to make a point to like an OS kill function, pretty much just make it, make the task kill itself. rest of the registers, you can just put a random value. And then once you're done, oh gosh, sorry. Well, once you're done, you need to update the TCB's stack pointer so that is pointing to wherever the stack last pushed, which is did that make sense of like how the context or the state of the CPU is saved onto the stack, and how and why we're initializing it like this? If anyone has questions, just stop me. Okay, I'm going to start writing like the actual like how all the TCBs and this are implemented. Sorry that explanation took so long. So real quick, I'm just gonna initialize this. Pretty much, so I initialized this array of TCB pointers. Pretty much each index is a priority level. And let me switch over real quick to this. Okay, so right now that array of TCB pointers that I just made is pretty much I'm implementing this part. So each priority would be an index in that array of TCBs and TCB pointers, and then it will point to a certain TCB. And then real quick, this run pointer. So the scheduler will like set this run pointer. So this is just pretty much a variable pointing towards like, oops. Thanks, Rishi. This run pointer that I have right here, it's pretty much a TCB pointer that's pointing to like the currently active thread. And yeah, I will switch over. There's one more variable called pointer, and that's for the scheduler. Okay. I'm gonna try to finish this up real quick, but after the stack is initialized and like the PC portion of the stack holds the task that it wants to run, and then LR holds the OS code, and then so forth. The main thing left to do is add it to the active list of priorities. So to call on the priority, okay, so pretty much when like I mentioned before, whenever like the add task and the multiply tasks were created, it's just setting that list array of pointers to the TCB that's related to. Also keep in mind that you should have a bunch of checks beforehand. That's where all the bugs come, not checking the null pointers, and later on like the OS would dereference a null pointer. So just make sure if whenever you implement your own that you actually check if anything is null and don't do anything if not. Okay, and then yeah, there's more stuff that you can do, but this is pretty much it. Just saying saving the whole context into the stack and then saving the TCB into your active priority list. And then OS launch is pretty much going to call like scheduler. It's going to call the scheduler and the boot function. So usually you don't, I guess in your own RTOS, you don't really have to if you don't want to. I usually make a scheduler. Make a scheduler function that returns like a certain TCB, depending on how you want to schedule it. We can go into that a bit later. So, okay. All right. I'll write the context. So I guess for the rest of the time, I'll show like how the context switch happens, like what you need to do in the dependency handler, and then I'll go over all the semaphores and how, like, whenever you block, how it's like going to be, how the node is going to be taken out of the active priority list and then into like the blocked list. If anyone has any questions or anything like that, just stop me. Right, so the dependency handler, that's like where the context switch actually happens. So the switching, or like updating the CPU to have, or saving whatever the CPU has, and then updating it with the new values of the different thread. First, you would, so these functions right here, they're pretty much just disable and enable interrupts. We don't want anything to interrupt in between, or else like the register values will be switched, and some of them may be switched and it could have like undesired consequences. Main thing is, so right here, I mentioned earlier that right before the handler function ever gets called, the processor pushes these registers onto the stack just automatically. The thing is, we need to push the rest of these registers. All right, I can just write this code real quick, but basically, I'm going to get the current stack, or I guess the current TCB. Right now, I'm getting the current TCB. So early here, we defined the struct. So at index 0 of the TCB is going to be a stack pointer. So right now, I'm just getting the stack pointer of the currently running thread. And then I'm going to store, skip the step, the important step that I just crossed over. Okay, so the first thing is I'm pushing the rest of these registers in order to save the whole context of the CPU. And then wherever the CPU, the stack pointer is at right now, in the stack pointer register, or it's R13, if I remember correctly. Let me know if I'm wrong though. Right now, I'm getting the address of this TCB, of the currently running thread's stack pointer. And I'm just going to save whatever the stack pointer is right now. Oops. Here. So after I push push these registers, the stack pointer changed. So I need to update this thread's stack pointer value so that whenever we get back into this thread, we can have like we have a reference of where the stack is. All right, this may be a bit boring. Okay, all right, let me explain this real quick. So this part pushes the rest of the context. This part stores the current SP value and saves it into the TCB field. This part, the reason why we have a next TCB pointer is usually whenever you call the scheduler, we would update the next TCB pointer. Because even though the scheduler was called, it's still technically there's still the thread that's currently running. There's still a thread running, and we still need to know what it is. So that's the reason why we have another variable. It's just so that whenever a context switch does happen, then we can then whatever is in here will be the new thread. Okay, so this is just this one is literally just replacing run t. It's just doing. It's just literally doing this. And okay, this one right here. Let me gather my thoughts real quick. Okay, so so currently, like all the register values are not through R15 and the PSR. It's still for the previous thread context. So right now you want to switch it to the newest, the next TCB thread. So right now this is updating the stack pointer so each thread has its own stack pointer, which is saved in the TCB. So we're just updating it so that we can have a reference of popping off like the new context. And this is just popping off. So the SP switch. So right now the stack looks like this in another thread. Imagine this is like in another thread. So you want the user or the handler needs to pop these registers. And then once you exit out of the interrupt, all the rest will be popped. Did that whole process make sense, or was it a bit confusing on how I explained it?
Makes sense.
Okay. Well, if anyone has questions, just let me know. But this is literally like your context switch, switching all those registers from one thread to another thread.
You're only pushing 2 registers, by the way.
Thanks. All right. Any other comments or questions? So this is literally how the context switch occurs, and then I'll show you whenever you start going with semaphore. So whenever you need to trigger this, which is from blocking. All right. Real quick, I can do this later, just for the sake of time. But OS boot is called in the OS launch function, which is to literally like just start the OS, to start running the OS. The thing is, we need to do a context switch. The thing is, it's not like, I guess, but we need to do it, but not in the terms of like, oh, I guess you can do it in the terms of an interrupt, but this OS boot function is just doing a context switch, but it's doing it in like the foreground thread. So not in terms of a interrupt. quick. Okay, so to actually like explain like when to trigger this context switch, I'm going to go over how semaphores are implemented. And a semaphore is literally just a counter. And then, there may be some max limit or like the max number of resources. So like a mutex, only one thread can have this resource or more depending on what you need, but most of the time it's only one. So the max will be one or something like that. And then okay, so this is how like all the blocking stuff works. The thing is, whenever you block a function, we need to save it, but we can save it in just like a generic like blocked list, but that's inefficient. And you can, and also if you trigger or set a semaphore or post it, that means you want to have like whoever is waiting to be unblocked. So whoever's waiting for that particular semaphore to be unblocked. So usually semaphores will have its own blocked list. And to further optimize this, you can have this like in a priority based, or if not, if you just want to keep it simple, you can just have it as a queue. And each time someone waits for the semaphore, it will just append its TCB to the queue. RTOS, we just do wait and signal, but in terms of like Nucleum, you will see pend, which is to wait, so like pending or something like that, and then post is to signal. And the init semaphore function is pretty much just resetting all the values, making everything null, and also I guess record how many resources or threads can access this semaphore. So there are multiple types of semaphores. There are binary semaphores and counting semaphores. There are also mutexes, which is just another version of semaphores. So with binary, for example, only one thread can access that semaphore. So this will be, you will pass in a one. So, and also mutex, you will just pass in one. But say you want to have like, you're allowing, I don't know, 4 threads to access this semaphore, then you can put this to 4. And so that's just the different versions. So also, every one of these needs to be atomic. There are a bunch of like functions that are atomic functions. So like, I don't know, clear and set and so forth, where like everything is just one instruction. In terms of ARM and microcontrollers, the most atomic thing, besides like individual instructions that will get, is disabling and enabling interrupts, because that's the only, interrupts are pretty much the only way to, I guess, create a critical section. Okay, so so whenever you wait or you append for a semaphore, just like the example I showed, where when you're going to check and see that the semaphore is available, and if it is, then continue running. If not, then you should block. Block and allow another thread to run. So pretty much, I guess, so an OS wave function will or OS pend or sum for pend or whatnot. I'm just going to copy code now. This is a bit boring. I'm editing the wrong thing. This one. Okay. This is like pretty much the gist of what you call semaphores. So whenever you wait, you're subtracting. I guess so. You have a value of like if it's less than if it's greater than 0, then that means that you or there's a semaphore available. Or if it's 0 or more, there's a semaphore available. If not, then you should block yourself. And the signal is just going to increment and increment the semaphore. I can explain semaphores more in depth later. There's like a whole different it's like a whole topic in RTOS just dealing with semaphores and purpose sections. For okay, but if a semaphore is not available, if the semaphore is not available, then we should block the task. If it and whenever you post it, we should unblock any waiting tasks. So whenever you block a task, we're pretty much going to be so the currently running TCB is stored in this variable. Okay. Sorry, this is so messy right now. If you remember from the demo from last week, whenever whenever the OS sees that this task is unavailable or this thread is unavailable, then it should block and remove itself from the priority list. So the block task is literally just moving the TCB, removing the TCB from the active priority list that we have right here. So each level is a priority, and then inside the Okay, so this right here is removing it from the active priority list, and this line right here is appending it to the semaphore's blocked TCB queue. And unblocking is literally just reversing this. It's removing it from the queue and then adding it back to the priority level that was at. I guess just for the sake of time and just not trying to be boring or make it more boring, I want to write this, but if you want to see it later, then I can, I guess, type it out afterwards. But does this make sense on like how the linked listing manipulation is working? After this.
Wait, so do you have one linked list for active and one for inactive?
So you have one linked list, I guess an array of linked lists for all the active, so each priority level. And then every semaphore that you make, it's you're I guess creating like a different blocked or deactive or inactive list. Does that answer your question? So you have one active list or one main active list, which is like all the priority levels. And then for every semaphore you make, you're making another blocked list or inactive list.
Okay, and then that's like the list of tasks that are blocked by that semaphore.
Yeah. Yeah, so like right here in this example, so this count semaphore right here, it will look similar to like the struct that we just made, which has like a queue of TCBs that are blocked. So whenever this add task gets blocked, it's going to add itself into the TCB for this add task will be placed into the count semaphore's waiting list or waiting queue. And then if you had another semaphore, then you would then it would be added to that semaphore. And then whenever you signal it or post it, then it's going to check the next, I guess, available, or the first person in the queue or first TCB in the queue of that semaphore. It'll remove it and then put it back onto the active array or active priority list.
Okay. So one task can only be blocked by like one semaphore at a time. Like you couldn't make semaphores.
Yeah, right. Yeah. Even though we have like start and end critical here, we're going to have to enable interrupts whenever we block so that we can perform our context switch. So it's just going, and then whenever like it comes back, it's just going to loop here until it's available. But most it shouldn't come back though. I guess, and then OS kill is literally just removing the TCB of the thread that's going to kill itself from the active priority list. All right, there's like a lot more stuff that we can go over, but hopefully that gives an idea of how an OS is implemented in code and how it's doing all the context switching and the register manipulations. But does anyone have any questions, or if there's anything that I sort of skimmed, then you want me to go into more detail? Also, was this helpful? I feel like it might have been a bit boring looking at someone watching, typing code very slowly.
It's really helped with the context switching mainly. I think that was one of the big things that I didn't really get in terms of implementation.
Sweet. All right, well, I'll be in the BPS Zoom call after this if anyone has more questions. But if not, then everyone's free to go. Hopefully this was helpful and not too boring.